In this video, I'm going to determine the intervals on which this function is continuous. So first note that this part of the function will be continuous on its domain. Its domain is actually all real numbers, and it's defined to be this for x less than 0. These two are constant functions, which are continuous everywhere. And this is a rational function, which is continuous on its domain, which includes all real numbers except 1. And we've just defined it to be this function when x is greater than 1, so it's continuous on that piece. However, there could be problems at the breakpoints. So we could potentially have problems at x equals 0 or at x equals 1. So we need to check whether the function is continuous at 0 and 1. So let's first determine whether the function is continuous at x equals 0. So we need to first consider the limit as x tends to 0 from the left, and we'll use that part of the function, and then the limit as x tends to 0 from the right, and for that we'll use this part of the function. So for the limit as x tends to 0 from the left, we have the limit as x tends to 0 from the left of e to the x minus 1 over e to the x plus 1, which is e to the 0 minus 1 over e to the 0 plus 1, which is 0 over 2, which is 0. And for the limit as x tends to 0 from the right, the function is defined to be 0 as x tends to 0 from the right. And the limit of 0, well, that's just the limit of a constant, and that is 0. So the right and left hand limits are equal. So that's great. We have one more thing to check, and that's the function value at that point. And the function value at 0 is defined to be here, when x is 0, f of x is 0. So that's also 0. And since the limit as x tends to 0 from the left of f of x is equal to the limit as x tends to 0 from the right of f of x, and that equals f of 0 because they all equal 0, this function is continuous at x equals 0. So we determined that the function is continuous at x equals 0. Looking again at the function, we realize there could possibly be a problem at 1 because it's defined differently on either side of 1 and then at 1. So we need to check the limit as x tends to 1 from the left. We'll use that. And the limit as x tends to 1 from the right, we'll use that. And then this is the function value at 1. So again, the limit as x tends to 1 from the left of f of x, that's the limit as x tends to 1 from the left, 0. And that's a constant function, so that's just 0. Now let's look at the limit as x tends to 1 from the right. So again, we're going to use this piece. All right, so we're looking at the limit as x tends to 1 from the right of x cubed minus x squared minus x plus 1 over x minus 1. Now, before we do anything, let's just check our type. So if I plug in x equals 1, I get 0 on the numerator and 0 on the denominator. And that is an indeterminate form. Now, with an indeterminate form, we need to do some algebra, okay? So one thing you could do, you know that x equals 1 is a root of x cubed minus x squared minus x plus 1, because when you plug it in, you get 0. So that tells you that x minus 1 is a factor. So you could do long division or synthetic division. But what I'm going to do with this one, I'm going to just do a little factoring by grouping. So I'm going to rewrite this as the limit as x tends to 1 from the right I'm going to pull out an x squared, and I get x minus 1. In the first piece, I pulled out an x squared there, and then I'm just going to pull out a minus 1 in this piece, and then I'm going to get minus x minus 1, and that's all over x minus 1. And applying the distributive law, this becomes x squared minus 1 times x minus 1 over x minus 1. Or you could do long division, and if you did long division, x minus 1 into that, you would get exactly x squared minus 1. You would get the same thing. But the whole point is now I can cancel those x minus 1s, and it will no longer be an indeterminate form, and so I could evaluate the limit. So I get that this is the limit as x tends to 1 from the right of x squared minus 1, and that's just a polynomial, so I can just plug in 1 and I get 1 minus 1, which is 0. And that's good because that is the same thing that we got when we did the limit as x tends to 1 from the left of f of x. We got 0 in both cases. So the function passed the first test at x equals 1 to be continuous. The right and left hand limits are equal. But there's another thing we need for f to be continuous at 1. The right and left hand limits have to also equal the function value. The limit of the function has to equal the function value at the point. So let's go up and check what is the function value at the point x equals 1. And if we look, the function value at the point x equals 1 is actually 3. So f of 1 is 3, and that is not the same as the limit as x tends to 1. Therefore, this function actually is not continuous at x equals 1. All right, so let's write that down. So f of 0, sorry, not f of 0, f of 1 is 3, and that's not 0. That does not equal the limit as x tends to 1. The right and left hand limits are equal, so I do have the limit as x tends to 1 of f of x. Therefore, the function is not continuous at x equals 1. And it was continuous at 0. We checked that already, and continuous everywhere else. So we can end this. We were asked to give the intervals on which f is continuous. So our solution, our final answer, f is continuous everywhere but 1.